let's dive right in. We've got a lot to cover today. Our agenda is we're going to do a real quick intro, and then we're going to be spending a majority of our time looking at Simple Store. It's straight from the HUFF project template. And then after that, we're going to spend a little time looking at an optimization challenge. And hopefully at the end of the session, we have a little time for Q&A. I'll also be checking the audio Q&A chat for questions and periodically check on those. So quick intro, HUFF, created by Zach Williamson and the Aztec Protocol team. They wanted to build an elliptical curve arithmetic library, but they needed to be more optimized than what Solidity could offer. So they decided to write it in pure EVM bytecode. But the thing with writing applications in bytecode is that there's a lot of challenges. There's a lot of annoying things that we're going to actually talk about today. So what they did was they developed a set of tools to assist with writing pure EVM bytecode applications. So that's kind of a common misconception that I just like to address for a second is I know we call HUFF a language, but in actuality, when you're writing HUFF, you're just writing pure EVM bytecode. And HUFF is a set of tools that kind of alleviate some of the pain points involved in writing that. So yeah, it was originally written by the Aztec team, and then last year, Jet with Vex and ref cells led kind of an effort to rewrite the HUFF compiler in Rust, and that is what we use today. So if you're a new beginner, I would recommend starting at the huff.sh. It's got all the links. It's got your Discord, GitHub, Twitter, and the docs link. And then there's this awesome HUFF repo that I maintain. It's got a lot of links to articles as well as a lot of different HUFF projects you can check out or contribute to. And if you just want to do a deeper dive on the EVM, I've got links to articles by Knox, Jean Cavallera, and Negachi that I think are really great deep dives on the EVM. If you just want to, if you just want to kind of jump in and start writing up some HUFF, I would recommend you git clone the HUFF project template, get the Foundry test working, and then from there, I would do the add to tutorial that I've linked, followed by the hello world tutorial. And after that, you will have the basic set of skills to really tackle anything you want. So that is kind of the path if you just want to learn by doing. So let's start off with the simple store. As I mentioned, this is straight out of the HUFF project template. This is like the example code that it comes with. And I've created a repo, so let's pull it up. It'll be easier to view in my editor. So let's look at the Solidity first for what simple store is. Super simple. It's just a storage variable called value with a function to set it and a function to get it. That's it. That's what we're going to be looking at in HUFF. Okay. So here is the HUFF code. Let's start at the top. We've got this interfaces section where we define all the external functions, very similar to interface in Solidity. And we're going to talk about what this is useful for in a second. We've got the storage slots section. This is how we define a constant. We're going to be talking a little bit more about that. And I'm going to skip over this free storage pointer thing. We're going to come back to that as well. And then you've got your methods. So we're going to skip over these first two methods and go straight down to main. So main is always going to be your kind of entry point into your HUFF contract. So when the HUFF compiler compiles your HUFF code, the first instruction in the main macro is going to be the first instruction in your contract. And I just want to take a big step back for 1 second. I've got die up here on Etherscan. I just want to make sure everyone's on the same page with regards to what bytecode is. Okay, so you've got your Solidity code here. I'm sure you're all familiar with that. And then you got all these weird numbers down here. Okay, so let's pull up EVM codes. We're going to be using EVM codes a lot today. So here's a bunch of numbers here's a bunch of those similar numbers, okay? What they are 2-digit hexadecimal numbers. And if we go to the opcodes page in EVM codes, we can see that every opcode has a corresponding hexadecimal number. So for example, push 1 is 60, okay? And what that instruction does is it places a 1-byte value onto the stack. I'm sure you probably know, the EVM uses a stack. If you don't know what a stack is, then I don't think that this presentation is for you. All right, so here we are back here. So let's look at these again. 60 is a push. When you are pushing 1 byte, it expects that the next byte be the value you are pushing. So this is going to be push 1, 42. So push a 42 onto the stack. And then we got push 1 again, and we're pushing 0 onto the stack, followed by 52, which is an M store. And then we're pushing a 20, and then we're pushing a 0. And finally, F3 is return. And we could switch to mnemonics, which is much more human readable. These are the codes that we just saw in mnemonic form. And this is also very, very similar to what HUFF looks like. HUFF almost looks identical to this. So now with that in mind, let's go back to HUFF. So before we dive into the instructions here, I want to just do an overview of the main macro. So, well, first of all, I'd just like to say that the HUFF compiler ignores white space. So you can have your instructions, separated by a space horizontally, or you can have them vertically. Some developers like to group instructions together on a single line, instructions to go together. So that's how this is set up. But just looking at it, we've got what we're going to do is we're going to pull the first 4 bytes out of the call data, which is the function signature. And then we're going to check if that function signature is equal to the function signature of set value. If it is, we're going to jump down here and execute the set value macro. If not, we're going to check if it's the get value macro. And if it's neither of those, we're going to revert. So as I mentioned, the white space doesn't really matter. But I think for a presentation, it's a little bit easier to look at them stacked vertically. So I just reformatted this and added some comments. So this is the exact same thing as what's in the repo. I just kind of messed with the white space and added some comments. So as I mentioned, the first thing we're going to do is we're going to basically parse the call data and pull out the function signature. So the first step in doing that is call data load. So let's go to EVM codes and see what call data load is all about. So call data load takes 1 input off the stack, which is going to be the byte offset from within the call data that we're going to be loading onto the stack. And so it will take that off the stack and it'll put something back onto the stack, which is going to be the 32 bytes starting from whatever offset you provided it. So we want the first 4 bytes. So we want to start from offset of 0. So now here we are, it just says 0, right? This is the first kind of little, feature of HUFF, is that instead of writing out the full push 1, 0, in HUFF, all you have to do is put the value, and HUFF will then, the compiler will then determine how many bytes the value is, and it will put the appropriate push. So in this case, it's just 1 byte 0. It's going to do a push 1 and a 0. So this is how we do push 1, 0, is we just put in 0 here. Now, one thing we like to do in HUFF that kind of helps manage the whole process, is really good with debugging and to kind of follow the flow, is off to the right, we'll manually keep track of the stack. We've talked about doing some automated tools that'll do this for you, and actually, believe it or not, GitHub Copilot is really good with these as well. But yeah, for now, it's a bit of a manual process, but it's extremely helpful, as you'll see. So after we push a 0 onto the stack, our stack contains 0. This is the first. Yeah. So this is the first instruction. So there's nothing nothing on the stack prior to this. So after we push a 0 onto the stack is just 0. So now we go to the next line, which is call data load. So what that does, as we saw, is it will take the 32 bytes of call data starting from, in this case, 0. And I want to take a second here to look at an example of call data. So as we talked about, what Solidity does when it calls an address, when it makes an external call, is the first 4 bytes is going to be the function signature, and then the next 32 bytes is going to be the first argument, okay? So we just said that we're taking the first 32 bytes starting from 0. So if we did that, it's going to be these 4 bytes, but then it's going to be the first 28 bytes of the first argument. So all this extra stuff here at the end is unnecessary, and we really want to just isolate the first 4 bytes. So how do we do that? We do that with bit shifting, specifically shifting right. So if we were to shift this to the right 28 bytes, which is 224 bits, then it would basically get rid of all this stuff. Oopsie. It would get rid of all the stuff to the right, and it will shift this all the way to the right, and it'll pad it then with zeros to the left. And just for convention, so that we don't have to always write a million zeros every time we write it, just so you guys know, we don't have to include the zeros when we're kind of referencing this value. We can just omit those, and this is the same thing as this. So here we are back here. We've just put a 0 onto the stack. We've loaded the call data onto the stack. So now we're going to push E0 onto the stack, which is 224 in decimal, which is 224 bits, which is the 28 bytes we want to shift. And then we call shift right. So now after this opcode gets executed, then we're going to end up with a signature. So we went to all that work just to get this onto the stack. This is the first 4 bytes of the call data. So yay, we've got the signature onto the stack. Now the next thing we're going to do is we're going to compare that signature to a known signature for set value. And if they're equal, we're going to jump down here to set value. So let's kind of go through. These are the groups of codes that do that. I've just kind of listed them vertically. So the first step is dupe 1. What dupe 1 does is it takes the first item in the stack and it duplicates it and it puts it in the top. So instead of just having the sig, we now have it twice. The reason we do this will become clear in a moment. So next up, we're going to do this equal, right? We want to compare the signature to the signature for set value. So we need to get the signature for set value onto the stack for comparison. So there's a number of different ways we could do it. I'm actually going to start with the first way. And actually, before that even, let's just take a quick look at how do we even get this function signature. Probably most of you already know. It's the exact same way that you would get it in Solidity. It's just the first 4 bytes of the KCAC hash of the string of the selector, which is the function name and the argument types. And actually, Sam CZ Sun's signature database can take HUFF function interfaces directly and give us the 4 bytes. So it's this 5524 number is the sig for the set value function. So one way we could get that onto the stack is just by hard coding it on there, right? This is one way to do it. Another way to do it would be to use a constant, okay? I kind of glossed over this other constant, but I'm still going to come back to this free storage pointer thing later. But let's say that we defined a constant set value funcsig, and we put that hard-coded 5524 here. Then we can access this constant anywhere within our code. And so this is another convenience of HUFF. So the way that we access constants is with this brackets notation. So when we put constant name inside of brackets, the HUFF compiler knows to put the value of that constant onto the stack. So it's very similar to constant in Solidity. So that's another way we could put it onto the stack if we want. But the coolest way to put it onto the stack is using this built-in HUFF function, this double underscore funcsig, and you pass it one of the functions that you defined above in the interface section, and it will just compute the 4-byte signature for you. So this is the way that we are pushing the function signature onto the stack, is by using this HUFF built-in function. There's some other built-in functions that maybe we'll look at later. So as of now, what we've done so far in the second step is we've duplicated the signature. We pushed the function signature for set value onto the stack. And now we're going to process this EQ, equal opcode. And what it does is it takes these first two items off the stack. And if they are equal, it will put a 1 on the stack. If they are not equal, it will put a 0 on the stack. So at this point, we either have a 1 or a 0 on the stack, and then we still have that sig that we duped earlier. So now I want to take a quick side journey and talk about jumps. Jump, you're probably familiar with the concept. In other languages, it could be like a go-to. Let's look at the jump in EVM codes. So remember when we looked at these byte codes at the very beginning? So the way that we kind of keep track of these is through something called a program counter. So this first number is referenced as 0, 1, 2, etc. It's kind of like line numbers in other languages. So what the jump instruction says is it says, okay, instead of going to the next line, the next program counter, it will take whatever you've put on the top of the stack as a counter, and it will, jump to that instruction next. So it's a way to go to other places within the code. So I have an example set up right here, okay? So I'm just gonna run it. So the first thing we do is we push an 8 onto the stack. And now we do jump. So what's it gonna do? It's gonna say, okay, I'm gonna jump to 8. And you have your instruction program counters listed down the left here. So it's going to jump down here. Now there's one caveat I forgot to mention about jump, is that the place where you're jumping to must have a jump dest opcode. Right. The place that you're jumping to must have a jump dest. So if we tried to jump, for example, to 7, it would error out. It wouldn't work. So in this case, let's see if it works. Yay, it jumped down here, and then it can go about doing whatever it wants to do. Let's say I'm getting a little feedback. Be sure that you're on mute, please. Miss Venthropic, maybe. So let's say I wanted to add a couple of instructions to this. Okay, so let's say I do like a push 1 OXO1, push 1 OXO2, and maybe, I don't know, multiply them, okay? So now let's run it. So we pushed our 1, we pushed our 2, we multiplied, now we push our 8 and jump. What? It errored. Why did it error? Okay, well, we're telling it to jump down to 8, but 8 is now this one, it's this push 1. Our jump dest got moved down to 0D because we added some instructions at the beginning. So now we have to, if we want to continue the same behavior, we have to go down here and update that to 0D. Now imagine you had like a dozen jump dests throughout your code and a bunch of jumps. And every time you add a single line of code, you got to update every single one of those. That is really annoying. So instead, in HUFF, we have abstracted this away through the use of something called a jump label. So here is a jump label. It's this syntax with a colon at the end. So when we write set with a colon, we're telling HUFF, hey, this is a jump label. So the HUFF compiler will replace that with a jump dest, and it will also when you reference the jump label, it will it will instead insert whatever program counter it corresponds to. So you don't have to constantly update the program counter you're jumping to every time you add a line of code. So I hope that's clear. Jumps are can be, as I mentioned, one of the major hurdles to trying to write a large application in bytecode, and I think HUFF handles them very nicely. So we've just done this EQ which is going to put either a 0 or a 1, depending on whether or not these signatures match. And then we've pushed the program counter for this jump destination onto the stack, okay? Now, I talked about jump. This is actually a jump I or a jump if. And so the jump just takes one item off the stack and it'll jump to that. The jump I takes a second item, which is, in this case, it's this conditional. And it's a little bit more robust than just 0 or 1. Actually, any non-zero value will cause it to jump. So if it's a 0, it won't jump. If it's a 1 or anything else, anything greater than 0, it will jump. Okay, so in this case, it's either going to be a 1 or a 0, but there are cases where you want it to jump if it's 99 or it's just anything that's not 0. So in this case, let's say it is a 1, then it would take these two items off the stack and it would say, oh, it's a 1, it's non-zero, so I'm going to jump down here, and then it would execute the set value macro. If it's a 0, then it will not jump and it will go on to the next line. So we've just gone through a set of instructions which will check if the call data, if the function signature in the call data is equal to a known function signature for set value, and if it is, it jumps down to this other section. So the second group of instructions does the exact same thing, but for get value. Okay. So after we've gotten to this point, we've basically handled the two functions, set value and get value. So the next line here does this 0, 0 revert. So let's just very briefly look at what revert is on EVM codes. It's down here near the bottom. All right, so revert. It takes two items off the stack, an offset and a size. And so, imagine you had like a revert, like a require with like some kind of an error string, and you wanted to return something when you revert. How you do it is you would load something into memory, and then you tell the revert instruction where in memory the return data is that you want to return with the revert, and it will return that when it reverts. In this case, we're not going to return anything, so we just push a couple of zeros onto the stack, and then we call the revert opcode. So what it means is that if somebody makes a call to this contract with a function with the first 4 bytes, the function signature, something other than set value or get value, it's going to revert. And so this is the normal behavior in Solidity. So imagine for a second that we didn't have this, okay? This is the kind of a common gotcha in HUFF is, people forget to put this in. In fact, I think I recently made a pull request to this very repo because this revert was not in here. So imagine we didn't have that, and imagine that somebody called this with something else, like, I don't know, hoagies, okay? So they call the hoagies function, and it goes through, and it says, is it set value? No. Is it get value? No. So it will just proceed to the next line, which is this set jump dest, which does nothing. And then it will proceed to the next line, which is the set value macro. So right now, without the revert, anyone calls it with anything other than set and get will automatically get them into set value. So imagine that as some like highly permissioned function, like some, auth function, very important function. It could be pretty dangerous. So it's, HUFF is full of foot guns, which is, and we're going to talk about this later. I think it's not a great, it's not a great way to write production contracts. But I think that one of the great things about learning about the EVM through HUFF is that you also get to see all of the guardrails that Solidity has in place for us. So for example, all this stuff that we've talked about, we just spent the last 25 minutes talking about, we don't even deal with that in Solidity, right? Like the function routing, the parsing of the call data, that's just all built in. The reverting, if you call some other function that's not available, in HUFF, you have to write all that stuff yourself. So this is just one of many things that we get with Solidity, and we're going to talk about more of those as well. But I just think it's so interesting. We spent so much time digging into things that just come right out of the box that we don't even consider in Solidity. And we haven't even talked about the meat of the core functions here yet. So let's do that now. So for set value, now one quick thing.
Yeah. Can we ask a question or only the?
Yeah, why don't we do a couple questions right now? Good idea.
Yeah. Okay. So I'd like to ask, why do we use the dupe one for? I mean, we get
Sure,
them.
yeah, I forgot to mention that. Good question. So if we didn't do a dupe one, where's my mouse? Okay, if we didn't do a dupe one, right? Let's say we didn't do this. So there would only be one sig on the stack. It gets used up by this EQ. So after the EQ, it wouldn't be here anymore, okay? And so it wouldn't be here anymore.
Got you. So it pops the first one, and we have two of them, so we're good to go. Yeah.
Yeah, so here's the problem is you get down here and you don't have the sig anymore. So we would have to pull it out of call data and do all these instructions again just to get to it. So it's a lot easier to just dupe it at the time and have it for use later. So that's, in my opinion, that's one of the kind of the fun things about writing EVM opcodes is writing bytecode is that some people say that's a downside is managing the stack, which of course it is, but it's kind of fun, I think, to kind of plan ahead. When you get into some really complex functions, it's almost like a little puzzle on how you put together your stack so that later it will have all the items it needs for the various functions you're going to call. So this is just a small example of that where we dupe something in advance that we knew we were going to need down here. But it can get a lot more complex, and that's kind of part of the fun of optimizing is setting up your stack in the perfect way. But that's why we dupe the sig there. I'm going to look through these questions, or if anyone else has any question that you are dying to ask, please chime in.
One question, like how to use nested jumps. For example, right now here we can see that set is there. For example, after two lines there is one more set, but that would consider like the parent set is calling the this is the destination instead of like it's a two nested condition. If so,
I'm sorry, I really didn't catch much of that. Could you speak up a little and say that one more time, please?
Okay, for example, here like in line number 57, there is a set like this is a go to. Okay, so if this condition happens, go to line number this which is 65. But for example, after this condition, if this jump does not happen in line number 60, we need another condition like jump to line number 63. Okay, that is before this set. That cannot happen, right? Because if in that case the parent set, which is the line number 57, will also think that okay, this the set on the next 2-3 lines is the destination instead of it's a separate go to condition.
So, I mean, we are doing a separate condition here. You would have to set up your conditional and do, and put the jump destination onto the stack and do jump if again. So, I mean, this is an example of doing a second conditional. You just have to set the stack up first. I mean, you could potentially set the stack up in advance, but yeah, I mean, it's basically the same exact process.
For
Why don't you
example, if
ping
you
me
want
on
to
that
see,
if you want to talk about that more later, we can take it offline.
Sure.
These other questions I'm seeing in the chat are more general purpose. I'd prefer to talk to at the end. So I think I'm going to move on. All right, so we just did all this work to do the function routing, parse the call data. Now, finally, we get to do the meat of it, which is to call the set value macro. So I want to talk just for a second about macros versus functions in HUFF. So all these things are macros. And what the compiler does with a macro is it basically just takes the code and it like copy pastes it right here. Okay. Like it's duplicating the code anytime the macro is called. I'm sure it sounds very, not optimized and wet and not great, but actually we are basically using up extra bytecode in the code length to optimize the runtime gas because HUFF does offer functions, but you'll notice that we usually don't use functions. We could call this a function. The difference, the difference between a function and a macro is that the macro gets copy pasted in there, as I just showed, but the function, it would actually insert like a jump to, so if we did use a function, then this would live only in one place. It would live only in one place, but we would have to put a jump here. It would, like behind the scenes, the compiler would put in a jump, it would put a jump test for the function, and then would have to put a jump test here and jump back. So it would save a little, it might save a little bytecode depending on how many times we use this function, but it's going to cost extra gas. So with Huff, like you're writing bytecode, it's very rare that we get up to the spurious dragon limit. So typically you're going to see we just always use macros because it's more gas efficient. So as mentioned, when we call this macro, and the way you call the macro is just put the macro name followed by the open close parentheses. It's effectively the compiler is just going to copy paste the code for the macro here. So what is this set value doing? So we're doing another call data load, okay? But this time, instead of starting from 0, we're starting from 4. So that should get you this whole first argument. This whole first argument. So we're starting at byte 4 and taking the 32 bits. So that's going to capture, that's how you capture the first argument in a call. So we do a call data load starting from position 4, offset 4. So that's going to put, the new value that we're going to be storing onto the stack. Next, you might recognize this as how we put a constant onto the stack. So now we get to talk about this free storage pointer thing. It's really, really a simple convenience thing. It's not that complicated. Like basically, we could put a 0 here, right? So the value, the first storage slot would be 0. So if we did that and we call this, value location thing 0, then doing this, we'll put a 0 onto the stack. And then when we do our S store, it would store the new value at slot 0 and be done with it. But imagine you had like a bunch of storage slots and maybe you're in the middle of developing it and maybe you like delete one and then you add one back and blah blah blah. What this free storage pointer does is it's just a very simple convenience. It's kind of like a curried function where it will return the current value, which if you haven't used it is 0, and then we'll add 1 to the counter so that the next time you call it, it will return 1 and then add 2 to the counter so that the next time you call it, it will return 2. So it's just a kind of a convenient way to manage sequential storage slots. So yeah, for this, it's just going to return a 0. So we'll put a 0 on the stack, and then S store takes in 2 items. It takes the storage slot and the new value, and boom, done. That's how you set a value. So now we look at get value. If you want direct stack access, you definitely want to, oh, sorry. Okay, so get value, let's look at that macro. So again, we use that same constant value location. It's gonna put a 0 on the stack here. And then we do S load, and what it does, it says, hey, get me the value of the item at storage location 0 and put it on the stack. So right now, that value is on the stack. So what are we doing down here? Well, ultimately, we're trying to return that to the caller. So let's look at the return opcode real quick. So the return opcode, it's similar to the revert in that it takes an offset and a size. So basically it says, hey, I'll return, and do you want me to return any data? If so, well, I mean, no matter what, you have to give it an offset in memory and a size. So in this case, we're telling it take the value that's located at memory offset 0 and take the first 32 bytes. OX20 is 32 in hex. So in order to do that, we have to put something into memory. So after we've done the S load, we have the value on the stack, and we push a 0, okay? And so now you've got 0 in value. So now when you do mstore, what it's doing is it's storing the value into memory at offset 0, so that when you return it here, it will say, okay, I'm going to return this value that just got stored at location 0. I'm going to return 32 bytes. So so first of all, I mean, I'm sure you guys know that memory is just like one bytes array, basically. But one common misconception that I see people having is that Solidity has a certain layout for how it uses memory. It's like the first two words from 0 to OX40 is like scratch space, and then it stores the free memory pointer at OX40, and then it stores like can't remember the top of my head. There's like a default value for arrays, and there's a slot 0. EVM, when you're just using pure EVM bytecode, like you could do whatever you want. That's a Solidity convention, but we can do whatever we want. We can put things anywhere in memory. We don't have to, that whole layout is only used by the Solidity compiler. So here we could just freely, if we want, put it into at position 0. That's just something I just want to point out, is that Solidity memory layout that I'm sure you guys are accustomed to is only for Solidity. It's not an EVM thing. It's a Solidity thing. So that's it, guys. That is the simple store example, and I think that we've really touched on like all the major aspects of HUFF. Okay, we talked about how we push things onto the stack. We talked about how we like to track our stack in the comments. We talked about constants. We talked about built-in functions. A couple other examples of built-in functions. We can get an event hash. We can get an error, which is very similar to a funcsig. Write pad, I like that one, so you don't have to write a bunch of zeros to the right if you're trying to have a write padded value. So there's a number of different built-in functions you can use. We talked about jump labels, we talked about macros and functions, and we talked about that free storage pointer thing. So to be honest, this is like 99, maybe not 99, but it's a majority of the functionality of HUFF right there. There are a couple more advanced concepts that are out of scope for this presentation, but this is really like the meat of what HUFF is all about. We can do a couple questions now before we go into the optimization challenge. I'll read through here or chime in if you want to ask.
Yeah, I'd like to ask another one, if possible. So unlike storage, we don't have like a memory management using HUFF, right? I mean,
that's right.
Built in.
That's right. Yeah. You manage your own memory.
Yeah.
Yep, absolutely. So every time a new external call is made, you'll get a new context with, a clean slate of memory. But while you're in that context, you have to manage the memory yourself.
Yep.
I'm just reading through some of these questions. I think I'm going to probably address most of these at the end. I don't see anything that's really directly related to what we've been talking about here. Is it easy to test out HUFF contracts? Yeah, like
I have a question.
Oh yeah, please.
Yeah. Could you talk about the takes 0 returns 0 statement?
Sure. So I intentionally avoided talking about that because it's a little bit confusing. It doesn't do anything. First of all, at least at this point, our compiler doesn't do anything. It's just helpful for developers. And remember how when we looked at some of these opcodes in EVM codes, for example, let's look at a better one, like maybe, how about call data load? Yeah. So remember how we, where did it go? We're gonna look at shift right. So remember how in shift right, we put two things on, it takes two things on the stack. It takes the number of bits to shift, and it takes a value, and then it outputs one thing onto the stack. It's the same kind of a concept. Basically, when we write a macro, just as a kind of like a heads up to other developers, we tell it how many things it takes off the stack and how many things. When it says returns here, it doesn't mean return in the context of like what the function is returning from the call. It means what it's returning to the stack. I know it's a little bit confusing, but again, this is very informational. So all of these, so for example, this first one, and these are just also not good examples of takes and returns because we're in both cases is 0, 0. Like this set value does not expect there to be anything on the stack, and it's not going to take anything off the stack. And when it's done, it's not putting anything back. But like, let's say that, for example, I set up like an internal, let's say that I set up like an internal function to help me for whatever reason. Like, let's say instead of doing this, I just want to call my internal set value macro. So, or let's say, yeah, let's say we did a call data load, and then we want to call the set value as a separate thing. So in this case, okay, we put the value from the call data onto the stack, and then we would call set value internal method here. Let me put the underscore. So in this case, we are taking one thing off the stack. We're going to take this value off the stack, and in this case, we're going to return nothing because we're going to. Oh, actually, we're taking two things off the stack, and we're returning nothing because at the end we're not putting anything back on the stack. So in this case, we would have this takes two, return 0. In the case of get value, if you did a similar thing, like if you made this whole thing an internal. And you just called it, oops. Let's say you just called it and then you did the return. Let's say you just did the return within the, quote unquote external function, and you call it here. In this case, it would expect nothing on the stack. It takes nothing off the stack, but in the end, it's going to add something to the stack. So we would say returns 1. So I really don't want to get too deep into this. I hope that's a good enough explanation. I know it's a bit confusing. It's not actually used by the compiler, but it's just an informational thing when you're, dealing with a lot of internal functions. It helps to identify, what is the expected behavior of the function you're writing. And there was a question in the chat about testing. So it's a little bit out of scope, and we're kind of getting a little bit later on time than I'm feeling comfortable with. So I'll just quickly say that, look at a couple of tests here. We have this thing called Foundry HUFF, which comes with the HUFF project template, and it has a thing called HUFF Deployer, which will it will compile the HUFF code, and then it will deploy it for you, and then you could just do your regular Foundry tests. And we also have some test helpers that I'm probably not going to get into today. It's a little bit, maybe if we have time later we can look at it, but there's also some helpers that they can help with testing. So unless anyone has any dying questions, I would like to move on to the last kind of thing I'd like to talk about, which is this Colat's puzzle CTF. Somebody mentioned something about this in a Spearbit Discord channel, and it kind of nerd sniped me. I kind of got into this and started doing it. It's this challenge by Quill CTF They call it a hard. I don't know if it's. I don't really think it's a hard. I mean, maybe it's more like a Spearbit medium, or maybe even like a easy medium. But it definitely is in a very illustrative example of how to optimize something. So I've copy pasted this into the editor over here, and the setup is basically there's this Collatz puzzle contract that's been deployed. And what you're supposed to do is you're supposed to call the call me function on that contract and give it an address. It's the address of your solution, okay? And we'll talk about what your solution does in a second. So basically what it does, this call me thing, it iterates through a bunch of numbers. And for each of the numbers, it has an internal function up here called Collatz iteration, which is super simple. It just, you pass it in a number. If it's even, it divides the number by 2. If it's odd, it returns 3 times the number plus 1. So for every number within this loop, it will call its little function up here. And then it calls your solution. It calls the same function on your solution, and it just makes sure that the 2 numbers are the same. So basically, your job here is to write a contract that has this function, Collatz iteration, that will basically do this. Very simple from a mathematical perspective. Now, there's a couple caveats. One is that your code must be less than or equal to 32 bytes. So this instantly rules out a Solidity contract. I think, just this in pure Solidity is probably going to be over 300 bytes. It'd probably be less if you did it like in Yule in the fallback, but I think it's still going to be way, way over 32. So when I saw this, I immediately thought, okay, I'm going to just craft a contract in HUFF, and I should be able to get under 32. It also has a runtime gas limit of 100, but when you write this in HUFF, you're not going to get anywhere near that. So this ended up not being a concern. So the concern was really, how do we get the code size under 32? So let's look at how we wrote this. This is my first attempt, like the kind of the naive approach, this Collatz 0. So here's what we're trying to do. We're trying to write a contract that has this Collatz iteration function that does this thing up here. So first of all, remember how we spent all that time over here in the simple store example, parsing the call data and checking and routing to different functions? We're going to just skip that. Okay, we're not going to do any of that. We're going to assume that whoever calls this contract wants to call the what's it called, Collatz iteration function. Okay, we're just going to completely ignore any kind of routing. Now, is this something you want to do in production? Probably not. Is this a major foot gun? Yes, because you could call this with anything. Like, let's say that you could call it with anything you want. You could call it with hoagies, and it's still going to run. It's still going to run the same code. So this is not something that I would recommend for hoagies. This is not something I would recommend for production, but it is something that I would. This is something we could do for a nice little optimization challenge here. All right, so back to the code. So we're skipping the routing. And so the first thing we're going to do is we're going to load that first argument. Remember, you pass in a number, and so this will put that number onto the stack. It's the same thing we used in simple store. So the first thing we're going to do is we're going to check if it's even. It's basically nmod 2 equals 0 would mean it's even. So let's look at it from a high level before we get into the actual codes. We check if it's even. If it's even, we're going to jump down to here. If it's not even, we're going to process the logic for being odd. And then after we process the logic for odd, we're going to jump down to this thing I call ret for return. And then the last step will be to, put the new n onto the stack, put it in memory, and return it. So let's just look at this a little more closely. So first we're checking if n is even. We push a 2 onto the stack. We're going to dupe it because this is the order that it needs to be for the mod. And so once we call mod with n and 2 here, it will give you the result of n mod 2. And then we're going to check is this equal to 0? If it is, this will be a 1. If it's not, this will be a 0. Okay, so now we say, okay, if it's 0, meaning if it is even, so if this equals 0 and we do is 0, then it's going to be a 1 if it's even. Okay, so 1 will cause the jump with the jump if here. So if the n mod 2 is 0, means it's even, we're going to jump down to the even case. If not, we're going to do the 3 times n plus 1. So to do that, we push a 3 onto the stack, multiply it, put a 1 on the stack, add it, and then we push the ret and jump straight down here. Okay. And from here, we're basically just going to push a 0 onto the stack so that we store the new n at location 0. And then we're going to return the first 32 bytes starting at location 0 that we just stored. And if it's even, instead of multiplying by 3 and adding 1, we're just going to divide by 2. We do that by pushing a 2, and then we swap it because this is the correct order to do the division, and then we call the divide opcode. So I did that. That was the first pass. And first try, this was the first one. And oh, did I mess something up when I was collapse T? So what did I do here? Let's try it again. So it's failed. It didn't pass the bad code size. I added a console log in here. So we see that the size of the code that we just created in HUFF is 36. And we need to get it under 32 or less than or equal to 32. So let's go back to the drawing board and let's take a look at this and see how we can cut down the code size. So jumps take up a lot of not only runtime code, but also code length, okay? Because think about it. You got to have your jump destination. You have to have your jump opcode, and you have to push the program counter onto the stack to jump. So right there, there's like 4 bytes right there. So maybe more. I have to think about it. But I just kind of thought that if we could find out a way, if we could figure out a way to even get rid of one of these jumps, then we're probably going to make it under the 32. So let's see here. What could we do? So basically, what if we got rid of this jump? And so in the odd case, we just let it continue on into the even logic and divide by 2. So that kind of occurred to me. And so let's look at this algebra, right? We have, right now, we want it to be 3 times n plus 1. But if we end up letting it continue into the kind of the even logic and divide by 2, we could do that if we multiply the top part by 2. So to do that, instead of multiplying n by 3, we could multiply n by 6. And instead of adding 1, we could add 2. And then later, when we go through this even logic of dividing by 2, it's going to come back to what we wanted. And so that's all I did. Those are the only changes I made, that and deleting the jump. So all the stuff at the beginning is the same. We're still loading the off the call data, and we're still checking if it's even or not. If it is even, we're still jumping down here. But here now, instead of multiplying by 3, we're multiplying by 6. And instead of adding 1, we're adding 2. And it's the same cost, both runtime and bytecode, to push a 1 byte value onto the stack, no matter what that value is. Well, I mean, as long as it's 1 byte. So this doesn't change, changing these numbers doesn't change our bytecode size. Getting rid of the jump down to return that ret thing, that does help us. So let's look at the odd case, because the even case remains the same. In the odd case now, we're multiplying by 6, adding 2. Then that resulting value gets divided by 2, which gets us back to the 3 times n plus 1 that we want. And then we no longer have that ret jump destination thing, and we just roll into returning the value. So once I did that, let's do a second try. Voila, it worked. We come up with a final size of 29 bytes. So that is how that is just a nice example of optimizing code length. We often optimize for runtime gas, so I thought this was a cool example. I will give you guys one super simple gas optimization that's very common. In fact, probably most of you already know it. But remember in the original pull at 0, whenever we're storing something or returning something, we have to push a 0 onto the stack, right? Like you're going to find that you push 0 onto the stack a lot. So how much does it cost to push a 0 onto the stack? If we go to EVM codes, we could see that push 1 costs 3 gas right here, okay? So there's another opcode called return data size. And what return data size does is if you have made any external calls during your, within this context, then whatever the size of the return data of that external call is, calling this opcode will return it. Well, we haven't made any external calls. And so when you haven't made any, calling this will put a 0 on the stack. So this is a slightly, so using the return data size is a slightly cheaper way of getting a 0 on the stack than doing a push 1 0. Push 1 0 is 3 gas, just calling return data size is 0. So that's just a very, very simple basic optimization that most of you probably already know. You can do this in YUL as well. If you're ever pushing a 0 onto the stack in YUL, you can use return data size to save 1 gas every time you need a 0. So that is it, friends. That is the majority of what I had, what matrix themed presentation would be complete without a I know HUFF final slide. We could start looking at the questions here, and also if you have anything you'd like to ask, please chime in. All right, so Moise asks, someone want to ask something?
Please go ahead.
Sure. All right, so Moise asks, can you explain how HUFF differs from other EVM compatible languages and what advantages does it offer? How does HUFF handle scalability challenges in smart contract? Okay, so I don't know a lot of other EVM compatible languages besides Solidity, YUL, and a little Viper. And I think now that we've gone through this, you could probably see that HUFF really isn't a language so much as it is just pure bytecode. So in terms of scalability, I mean, I think we talked about some of the things that HUFF brings to the table for writing larger applications in bytecode. But in general, I mean, writing things in pure bytecode is not scalable really at all. Do you think that low-level languages like HUFF will become mainstream? I don't think it will become mainstream, and I don't think it should. I mean, what I think I would really like to see, there's this thing called verbatim that allows you to put in pure bytecode, inject it into your code, but right now it only works with YUL. So it would be nice if we could have access to that within Solidity. And then, I kind of envision, having some bytecode snippets, like right now, we lean on like Soulmate or Open Zeppelin contracts that have been thoroughly reviewed. So imagine if we had like a highly optimized like NFT mint function that we could just like pop in through verbatim. I think that would be really cool. But I don't think we are going to ever, and I don't think that we should see HUFF become like a mainstream language for writing all your contracts. There's just too many foot guns. And that's the whole point of Solidity, is to, make things safer and easier to read. Any top HUFF extensions? Yeah, there is one. I think if you just search for HUFF, you'll find it, and it helps with the syntax highlighting for VS Code. That was a question about a VS Code extension. Is there any difference in terms of gas for contracts written in HUFF and YUL? I'm trying to think. I feel like HUFF, you have a little bit tighter control. I mean, in general, no. In general, HUFF and YUL are going to be very similar. But if you're injecting YUL as inline assembly, then it's going to come with some of the guardrails that Solidity comes with. So from that perspective, HUFF is just going to give you no guardrails, and also it's going to give you a lot of foot guns. So from that perspective, HUFF using HUFF or using pure bytecode might be a little more optimized, but in general, I mean, YOL is very close to HUFF. You just have control over the stack and jump destinations with using bytecode versus YOL. Under what conditions should we prefer HUFF over YOL? I think the conditions would just be like where you need that extra bit of control that I just mentioned. Can I use HUFF as a transpiler for higher level language? Where's the HUFF? Where in the I don't know. I don't know the answer to that. You probably can. I see Axix already responding to you here. So I'll let that thread go. Looks like you guys have been going back and forth. We're getting tight on time. Can HUFF be used offensively to exploit contracts? Sure. I mean, you could use whatever you want to write attacking contracts. It'd probably. I mean, it actually. I think there was a question, or maybe I haven't hit it yet. Like, is HUFF used in production? Generally, not. There was the one that I mentioned that Aztec did way back in the day. There's another one that is like a EVM. It's like an online EVM machine, which I can't remember the name off the top of my head. That's the one. Thank you, Madia. He just posted it in the channel. The high VM. That's exactly the one I was thinking of. But actually, HUFF is used a lot for MEV. I think, EVM bytecode, I should say. I don't know if they actually use HUFF, but bytecode, bytecode only contracts is used a lot for MEV bots. Do you think it's a good idea to use HUFF for building MEV bots? Hey, I just said, yeah. When translating one country, how would you approach that? What you do when I'm translating from Solidity to HUFF? Yeah, I pretty much would do it line by line. That's probably how I do it. But then it's kind of like this. You got to go line by line and kind of think it through. But then, as I kind of alluded to during the presentation, like you have to worry about the stack. So you may end up with this like really messy stack, and then you will then kind of iterate back and go back and do things that'll make the stack a lot cleaner. HUFF, ABI encode, decode replacements. I don't know of any examples. I think that's it, guys. I think that's all the questions. Yeah, this was fun to do. I hope you guys enjoyed it. And yeah, that's all I got.